Hello, I'm your TA. In this video, I'm going to share you my understanding of one-way ANOVA and two-way ANOVA with hand calculation. 1, 2 means that the number of independent variable. So we usually call these one as factors. So 1 and 2 means number of independent variable, which is factor. And A as ANOVA means the number of dependent variable. So as I showed in the previous ANOVA video, if I want to compare the mean of group, if I want to compare the group mean of the SAT score according to 3 teaching methods, we can compare teaching method 1, teaching method 2, teaching method 3, and we have dependent variable as test scores. This is my 1A ANOVA design. We have only one independent variable, which is a teaching method, and we have only one dependent variable, which is a test scores. If I want to compare how test scores are different according to both teaching method and learning environment, I can add one rows here. So learning environment number 1 and learning environment number 2. We have two independent variables here, teaching method and learning environment, and we still have only test scores as a dependent variable. So in this case, my independent variable, teaching method and learning environment, because we have two independent variables, which is two factors, that is why two-way, and we still have only test scores, which is one dependent variable, that is ANOVA. We want to know that how test scores are different from the groups according to the teaching method and learning environment. These are independent variable, which is factors. And because we have 3 teaching methods, there are 3 levels. And we have 2 learning environment, we call there are 2 levels. And we have only one dependent variable, which is test scores. Just for your information, I am going to explain what is one-way MANOVA and two-way MANOVA. Even we change it to the MANOVA, still M stands for the number of variables, dependent variables. So if I want to compare the teaching method 1, teaching method 2, teaching method 3, we still have only one independent variable, which is a teaching method with 3 levels. And because we have a MANOVA, we need to have at least 2 dependent variables. So for example, I will say math test score and verbal, and math test score and verbal test score, and math test score and verbal test score. Because we have 2 dependent variables, which is math test score, verbal test score, we call this one is one-way MANOVA. What if I want to compare teaching method and learning environment, we could add one row more in the bar. So this is learning environment number 1, learning environment number 2. We also have test scores for both math and verbal this way. In this case, we have 2 independent variables, which is teaching method and learning environment. So we have 2 independent variables, which is 2 factors with 3 levels for teaching method and 2 levels for the learning environment. And we still have more than two dependent variables, which is SAT, math score, and verbal score. That is, we call this design as two-way ANOVA. In both hand calculation table and SPSS result table, one-way ANOVA table has in the row treatment, error, and total. And sum of square, degrees of freedom, two-way ANOVA. My table has many rows. So for the treatment, we have factor 1, factor 2, and interaction effect. We call 1 times 2. This is for the treatment, and then error and total. We still have sum of square, degrees of freedom, mean square, and F values. So we need to calculate more than when we done in one-way ANOVA. So I'm gonna just simply explain what is main effect. Number 1 is by ignoring factor 2, we just think as one-way ANOVA. For factor 2, main effect for factor 2 can be thought as by ignoring factor 1, we can think as one-way ANOVA only with factor 2. This is only with factor 1. So teaching method example, we had teaching method 1, teaching method 2, teaching method 3, and learning environment number 1 and 2. So my main effect for teaching method is by ignoring learning environment, we are going to comparing my test scores according to teaching method. So we are going to comparing just teaching method because this is the one-way ANOVA we have done in the previous video. But main effect for factor 2, which is learning environment, is that by ignoring teaching method, we only think as the mean of learning environment. So we make the mean using this data, and we need to compare environment number 1 and number 2, and comparing these two. We can think as one-way ANOVA with learning environment. And interaction effect is, we are gonna think no interaction effect first. So difference across factor number 1. So if we make a graph, this is cell means. And if I have factor number 1, factor 1 is teaching method, for example. This is teaching method 1, teaching method 2, and teaching method 3. In the learning environment across teaching method 1, teaching method 2, teaching method 3, these are statistically same. So we can ignoring factor learning environment. So we can only average the green line and purple line, we can comparing with only one-way ANOVA. And there is another graph example so with a no interaction effect situation. In this case, there's also the difference between two learning environment situation is statistically same. So this is also there's no interaction effect situation. However, if we have interaction effect each other across factor 1, which is a teaching method here. For example, this is cell mean and teaching method 1, teaching method 2, and teaching method 3. My learning environment, first learning environment has this way. However, my learning environment 2 test score means are this way. In this case, the difference between learning environment across teaching method 1, 2, 3 are different. We have the most difference in teaching method 1 and we have the least difference in teaching method 1. In this case, we call this, there is interaction effect between factor 1, which is teaching method, and factor 2, learning environment. In these two graphs, the difference between learning environment is this one, this one, this one. The amount of difference is different according to the teaching method. And here is also, we have this difference in teaching method 1, but in teaching method 2, we have this amount of difference and this amount of difference for teaching method 3. So that is why in these three cases, we have interaction effect. I'm going to show you how to do a hand calculation using the formula. So for example, we have teaching method and learning environment, and keep in mind that our ANOVA analysis goal is comparing means. So we are gonna say learning environment is factor A. This is factor A. There are two levels, and I will call teaching method as factor B. And for factor B, we have three levels. So I will say factor A has, which is learning environment, there are two levels. So I will write this one as small a, the number of levels as small a. And we have teaching method, which is factor B. There are three levels. So I will write that number of levels for factor B is small b. And then we need to know the notation for the group means. So we usually write x something something bar. This is my grand mean. The first number is the row number and the second number stands for the column number. So this is the first row. This one is first row and first column. We call this group mean as x11 bar. This one is my first row and second column, x12 bar. This one is first row and third column. I will call this one as x13 bar. This one is second row, first column, x21 bar, x22 bar, x23 bar. And we also need our marginal means. So we usually call row means and column means. See row means first. We need to see this column. In this column, only the second number, which is the number of column 1, 2, 3 is different, and we have all ones in the first number. So we write as x1 dot bar because we keep 1 in the first number and the number of column keep changing. For my second row, we have 2 in the first number. However, 1, 2, 3, which is the number of column, is different. So we call x2 dot bar as my row means. And we need to see the column means. We need to see in this way. Here, 1, 2 is different, but the second number 1 is the same. So x dot 1 bar. In the second column, we have same 2's in the second number. However, we keep changing 1 and 2. So we put the dot here, x dot 2 bar. This is my second column mean. And x dot 3 bar. And we usually write grand mean as x dot bar. This is my two-way ANOVA table. For treatment A, sum of square can be calculated as B. This is the number of levels for factor B times the number of cells is number of each cells times sigma I is 1 to A. A is the number of level for factor A. And group mean. So factor A, we have group means. These are my group means for factor A. So xi dot, so I is from 1 to A. So x1 dot bar minus x dot bar. So we can rewrite this one as, because we have 3 levels for teaching method. So 3 times, and we don't know how many test scores we observed, times, because we have only 2 group means, x1 dot bar minus x dot bar squared plus x2 dot bar minus x dot bar squared. And my degree of freedom is the number of level minus 1. So we have the number of levels for factor A minus 1, which is A minus 1. And mean square is sum of square A divided by mean square error. Mean square for factor A is sum of square A divided by degrees of freedom of factor A, which is A minus 1. And for factor B, my formula is A, which is the number of level for factor A times n number of each cells times sigma j is 1 to B, which is the level of factor B. And for the factor B, my marginal means, which is column means, are x dot 1 bar. So x dot j bar minus x dot bar squared. So we can rewrite these cells because we have 2 levels for learning environment, 2 times how many, we don't know how many observations we have, times, because we have 3 group means x dot 1 minus x dot bar squared plus x dot 2 bar minus x dot bar squared plus x dot 3 minus x dot bar squared. This is how to calculate the sum of square for factor b. And degree of freedom is the number of levels for factor b minus 1, which is small b minus 1. Here is 2 because 3 minus 1 is 2. And mean square for factor b is sum of square for factor b minus degree of freedom of factor b, which is b minus 1. And for the interaction, we need to know SS cells equals SS interaction plus SS for factor A plus sum of square for factor B. We need to know this one. So for the interaction, we can write as sum of square cells minus sum of square error minus sum of square B. And we're gonna calculate the sum of square total first. Sum of square total is 1 to A, J is 1 to B, and N is 1 to K. K is 1 to N, X, I, J, K minus X dot bar squared. This is if we have observation data, which is teaching method 1, 2, 3, learning environment 1 and learning environment 2, and if I have 5, 7, some numbers, we have data observations, and up to we have 11. We need to calculate 5 minus grand mean squared plus the next two observations, 7 minus x dot bar squared plus up to 11 minus x dot bar squared. So we need to sum of square with difference between all observation and grand mean. Once we have SS total, we can calculate the sum of square error. So we can write sum of square error as sum of square total minus sum of square A minus sum of square B minus sum of square interaction effect. We can rewrite as sum of square total minus and sum of square A plus the sum of square B plus the sum of square AB. Let's see. This part is the same as this one. This part is same as this one. So we can rewrite sum of square error as sum of square cells. And degree of freedom of interaction effect is level of factor A minus 1 times number of levels for factor B minus 1. So we can write it as A minus 1 times B minus 1. Here, 2 minus 1 times 3 minus 1. And error is AB times N minus 1. A is the number of levels for factor A, B is the number of factors for factor B, N is the number of observations for each cells. And degree of freedom of total is A, B, N minus 1. The number of all the observation minus 1 is degree of freedom of total. And mean square for the interaction is sum of square interaction divided by degree of freedom of interaction, which is A minus 1 times B minus 1. And mean square for the error is divided by degree of freedom error, which is AB N minus 1. And mean square of total is sum of square total divided by degree of freedom of total. This is sample variance. My F observed value for the factor A is mean square for factor A divided by mean square error. So we need to divide by mean square error. And mean F observed value for B is mean square B divided by mean square error. F observed value for interaction is mean square interaction divided by mean square error. And my F critical values are, if my alpha is 0.05, we need to find F value in the F table with alpha is 0.05. For factor B is, I need to find in F table, my first degree of freedom is mean square for factor B, which is B minus 1, comma, this degree of freedom AB and minus 1. And my F critical value for interaction effect is A minus 1 times B minus 1. So A minus 1 times B minus 1. And then I need to find the degree of freedom for the mean square error, which is AB and minus 1. So AB and minus 1. That's it. In this section, I'm going to share you how can we set the null hypothesis and how can we calculate the F statistics and compare to the F critical value. So factor A, which is learning environment. For factor A, we had two, so my H0 gonna be population mean for A, which is a learning environment, are same, equals. So in the table, learning environment, to make a minor hypothesis possible, we need to say these are equal to this one. So we can write as mathematically mu of 1 dot equals mu 2 dot, assuming that we have A levels, mu A, and my my observed statistic is in the table here. My observed statistic is MSA divided by MS error, and we need to compare this one to F critical value with assuming that alpha is 0.05. My first degree of freedom is degree of freedom for mean square error A, which is the number of level of factor A minus 1, comma, degree of freedom of MS error is A, B, and minus 1. If F observed value is greater than F critical value, we reject the null hypothesis. And F observed value is less than F critical value, we fail to reject the null hypothesis. For factor B, here is my teaching method, assuming that we have B levels. So my null hypothesis is gonna be population mean, which is mu, for factor B are same. So let's go to the table. So to make a minor hypothesis gonna be possible, we need to compare these three column means are equal. So X dot number bar. So I can write this one as mathematically mu dot 2 equals up to mu dot B because we have B levels. My F observed value is, let's go to the table. This is my test statistics. So MSB divided by MS error. MSB divided by MS error. And we need to compare this number as a critical value with alpha is 0.05, with degrees of freedom is degrees of freedom of the number of level -1, comma, degrees of freedom of MS error, which is A, B, and -1. And for the interaction effect, A times B, my null hypothesis, just to say there is no interaction. And my alternative hypothesis is there is an interaction. It is very complicated to write mathematically, so you just write it as in word. And my F statistic is here for the interaction, mean square AB divided by mean square error. We need to compare this one as a critical value, assuming that alpha is 0.05, and my first degree of freedom is degree of freedom of interaction effect, which is A-1 times B-1, A-1 times B-1, comma, my second number of degrees of freedom is degree of freedom of mean square error, that is A, B, and -1. In all cases, F observed value is greater than F critical value, which means that in F graph, this is my critical value. After this line, this is the rejection area. If my observed value located in this area, we need to reject the null hypothesis. So when F observed value is greater than F critical value, we reject the null hypothesis. And F observed value is less than F critical value, which means that my observed value is located in here, which is not in rejection area. We fail to reject the null hypothesis. For two-way ANOVA, you need to check interaction effect first. You always start from the interaction effect. In two-way ANOVA, my first step should be test for interaction first. So if we have significant result, which is there's an interaction, we need to test for simple effect. But my result is not significant, which means that there's no interaction effect. We need to test for main effect. That is my second step. And according to each test for simple effect and main effect, we have significant result and not significant result. So in step 3, if my simple effect is significant, we need to do a multiple comparison, which is in chapter 12. And if there's no significant result, we are done. And tested for main effect, we have significant result. We need to do a multiple comparison. So which is in chapter 12. And if we have no significant effect, we are done. I hope this video is helpful for your understanding for two-way ANOVA.